We're told that three possible resonance structures for the thiocyanate ion are shown below. All right, there we have them. Based on formal charges, which of the three structures contributes most to the resonance hybrid of thiocyanate? And they've given us some extra information. They've given us the various elements in these resonance structures, and they've told us their Pauling scale electronegativity. So maybe that is going to be useful for thinking about based on the formal charges, which of the three structures contributes most to the resonance hybrid of thiocyanate. So pause this video and see if you can figure that out. All right, now let's work through this together. So there's really two things we want to optimize for when we're thinking about which of these resonance structures contributes most to the resonance hybrid. One, we want to figure out the resonance structures where individual atoms have formal charges as close to zero as possible. So let me write that down. Individual atoms have formal charge as close to zero as possible. As close to zero as possible. We're not talking about the charge of the entire ion. We're talking about individual atoms' formal charges. Close to zero as possible. And then the electronegativity is useful because we also want to see if there's any negative formal charge on an individual atom, that ideally that would be on the most electronegative of the atoms. So any formal charge, so once again, we're not talking about the charge of the entire ion, any formal charge, any negative formal charge on individual atom, ideally on most electronegative ones, or most electronegative one, electronegative. All right, now with these two principles, let's figure out which of these resonance structures get closest to these ideals. So to do that, let's just calculate the formal charges in each of these resonance structures. So the way that we do that is, for each of these elements, if you had just a free atom of it that was neutral, how many valence electrons would it have? And actually, let me make another column right over here, which is just the valence electrons. You could look it up on a periodic table of elements, or you might already know that carbon has 4 valence electrons, 6 total, but 4 in that second shell. Nitrogen has 5 valence electrons, a neutral nitrogen, 7 overall electrons, but has 5 in its outer shell. And sulfur has 6 valence electrons. And the way that we calculate formal charge of the individual atoms in each of these resonance structures is we say, all right, how many valence electrons would, say, sulfur, a neutral free sulfur atom, typically have? And we know that that is 6. And then we say, well, how many outer electrons are hanging out around this sulfur in this resonance structure? And the outer electrons that we see here, it's really from this Lewis diagram. We can see 1, 2, 3, 4, 5. So 5 electrons versus 6 valence electrons in a typically neutral sulfur-free atom. And so it's 1 less electron. So you would expect a +1 formal charge here. Another way you could think about it is typically 6 valence electrons, but we are only seeing 5 hanging out in this Lewis structure. So that's where we get our +1 from. Now we can do the same exercise for the carbon here. Carbon typically has 4 valence electrons when it's neutral. And in this Lewis structure, in this resonance structure, we can see that 4 outer electrons are hanging out, the same as you would expect for a neutral carbon atom. And so 4 minus 4, you have 0 formal charge here. And then for the nitrogen, we have 1, 2, 3, 4, 5, 6, 7. We can say outer electrons hanging out. Neutral nitrogen would have 5 valence electrons. So 5 valence electrons, we have 2 more than that. 5 minus 7 is -2. So since we have 2 more outer electrons hanging out than we would typically have for a neutral nitrogen, we have a -2 formal charge. Now let's go to this resonance structure here. So same idea. Here we have 1, 2, 3, 4, 5, 6 outer electrons hanging out the sulfur. Now that's the same as the neutral sulfur valence electrons. So here we have no formal charge. We could think about it 6 minus 6 is equal to 0. Carbon, we have 4 outer electrons hanging around from this Lewis diagram. And that's typical of the valence electrons of neutral carbon. So once again, 4 minus 4, we have no formal charge there. And then we move on to the nitrogen. We have 1, 2, 3, 4, 5, 6 outer electrons hanging out. Nitrogen would typically have 5. 5 minus 6, we have 1 extra electron hanging out, which gives us a -1 formal charge, the nitrogen right over there in this resonance structure. And then last but not least, in this resonance structure, we have 1, 2, 3, 4, 5, 6, 7 electrons hanging around, outer electrons hanging out around the sulfur. Neutral sulfur would have 6 valence electrons. 6 minus this 7, we have 1 extra electron. That's what gives us this -1 formal charge for the sulfur in that resonance structure. The carbon is still having 4 hanging out, which is typical of carbon, a neutral carbon's valence electron, so no formal charge there. And then the nitrogen has 1, 2, 3, 4, 5 outer electrons hanging out, which is equivalent to a neutral nitrogen's valence electrons. And so 5 minus 5, you have no formal charge. So there you have it. We've looked at the formal charges on all of these. And now let's look at these ideals. So individual atoms have formal charges close to 0 as possible. In this first resonance structure, we have 2 individual atoms whose formal charges are not 0. And in fact, nitrogen is quite far from 0. While in these other 2 resonance structures, we only have 1 atom whose formal charge is not 0. So I'm liking, just based on this first principle, I'm liking these second 2 resonance structures as contributing more to the resonance hybrid than this first one. So I will rule that one out. And then if we had to pick between these 2, we could go to the second principle. Any negative formal charge on an individual atom, ideally on the most electronegative. So in this resonance structure here, I guess the second resonance structure, the negative formal charge is on nitrogen, while in this third one, the negative formal charge is on sulfur. And we can see from this table that nitrogen is more electronegative than sulfur. So in the second resonance structure, you have the negative formal charge on an atom that is more electronegative, the nitrogen, than in this third resonance structure. And so this is the one that I believe contributes most to the resonance hybrid of thiocyanate for these 2 reasons.